This is lecture 9.3, which is all about weak base equilibrium and Kb. And I think if you're good at Ka, you're going to discover that this is just a same situation with one small variation. So if you haven't yet done so, go take care of these very short learning targets in your notebook first, and then restart the video and come on back and watch for some examples and some more details. Okay, so let's go. So weak bases are very much like weak acids in that in a situation in equilibrium, there's much more concentration of the weak base molecules than there are of the conjugate acid and hydroxide ions. Or if the weak base is the conjugate of a weak acid, then the conjugate of a weak acid, that's a molecule, sorry, it might be the anion of the weak acid, like A minus, in which case A minus is in much greater concentration than the conjugate at that point, and the OH minus. So what you're looking for here is watching for amines. This would be NH3 or some compound that's a CH3, maybe NH2. This would be what we call methylamine, or we could have a long carbon chain with lots of H's and an NH2 like so. All right, so you're watching for those as to fit this equation, or you're watching for the anions of weak acids, like maybe F minus or BrO3 minus, etc. Things that are the anions of weak acids. All right, so you're going to work this the same exact way. You're going to write an equation, you're going to write the Kb expression, you're going to write your ice chart, and you're going to solve for X. Then you're going to decide if you're going to use X to find pH, or if you're going to use the X to find the Kb. Okay, so we've got this same situation, and we're going to work backwards and forwards just like you did with Ka. The biggest difference, and the thing that you have to keep track of, is that at the bottom of your ice chart, the ion in solution that you care about is the OH minus, which will not directly give you pH. So if you're given pH, you don't directly get OH minus either. So you have to be really careful. You're going to go through the POH step, and I've outlined that for you here. Basically, you can kind of look through this, but to find pH, we're going to ice it. We use Kb to solve for X, which is then OH minus concentration. So we take the negative log of OH minus to find POH and subtract from 14 to find pH. Or some of you would rather use this negative log of OH minus. Sorry, before you take the negative log of OH minus, some of you would rather use your OH minus and Kw to go to H3O plus. And then you can do the negative log of the H3O plus to find pH. You can also do the same if you're given the pH. This is so that you can figure out what X is to solve for Kb. And if that's the case, you have to remember that you have to find POH before you can match it to the OH minus in your equilibrium line, which would be your X. So often I will subtract from 14 to find POH and then do 10 to the negative POH, but you could also find yourself using Kw, use your pH to go to H3O plus, use Kw to go to go from H3O plus to OH minus. If you're given pH, let me back up. You can use Kw to go to from pH to H3O plus, then from H3O plus using Kw to OH minus, which then equals X. So long story short, I'll show you both. Okay. All right, so let's look at this. An example here would be to find the pH. So in this case, we're looking for the pH of a 0.5 molar solution of ammonia. The first thing that I'm going to do is write the equation. And unlike with acids, where you kind of have a choice if you want to add the water, with a base, you have to add the water. I like to call these base hydrolysis equations because really the base is a weak base that's creating OH minuses because it's splitting the water into H plus and OH minus. Okay, so this is truly the water is absolutely necessary. So in this case, the base is going to accept the hydrogen from the water and become NH4 plus, leaving behind OH minuses, which is why this is a base. So this is definitely a Bronsted-Lowry base. If I have 0.5 molar ammonia, I'm not worried about the liquid water. That means before anything happens, I have no ammonium and no hydroxide. So now I have to go to the right because the zeros are there. So this will be minus x and plus x and plus x, which gives me 0.50 minus x, and x. And then I'm going to say that Kb equals the concentration of the ammonium ion times the concentration of the hydroxide ion over the concentration of the ammonia molecules. And I can set Kb equal to all those ion concentrations from the E line of my ice chart. So that would be 1.8 times 10 to the negative fifth equals x times x, or x squared, over 0.50 minus x. As before, this 0.50 is 10 to the negative first, and the Kb is 10 to the negative fifth. So that's a difference of 4 powers of 10, which means that probably this is going to be less than 5% dissociation. You can always check it once you're finished the same way. Solve for x and then divide x by your initial concentration and multiply it by 100, just like you did for Ka for the H3O plus concentration. So I'm going to go ahead and cross this x off in the hopes that it will be a small enough dissociation, which means I'm going to do 1.8 times 10 to the negative fifth times 0.5, and then take the square root. So when I'm finished, I'll have x equals 0.003. I need two significant figures, so 0.003 molar. And this is the OH minus concentration, because in this situation, x is OH minus at equilibrium. Okay, so we need to make sure that we're aware of that. If I want pH, I'm going to do the negative log of this will equal POH, because this is OH minus, which I wrote down as 2.5228. I'm not going to round to sig figs yet. And then pH would be 14 minus the POH, which would be 14 minus 2.5228, which I found to be 11.47712, a bunch of numbers. I have two significant figures, so this is two places after the digit, or after the decimal, so this would be 11.48 as a pH of my 0.5 molar solution of ammonia. Okay, so that's that direction. Let's go do one the other direction. This will be a quick video. So in this case, we have a 1 molar solution of sodium acetate, and you have to start to recognize that if you have a solution of an ion that could be the anion of a weak acid, then this ion is a weak base. So you have to start to recognize that. So in this case, I have the acetate ion. I'm going to write it the way you wrote it in first year chem, plus water gives me acetic acid. You could also write it as CH3COO minus or CH3COOH and OH minus. And I'm going to ice this, not worrying about the water. This is 1 molar. These are 0. I have to go to the right because those are zeros. So minus x plus x plus x. Remember, when you go back to KSP and KC and KP, you'll have to worry about coefficients again. So don't forget that. Right now, you don't have to, because we always transfer 1 hydrogen at a time. So this is 1 minus x and x and x. I'm going to say Kb equals the acetic acid, HC2H3O2, times the hydroxide over the acetate, C2H3O2 minus. And I'm solving for Kb, so that means I have to know x. So in this case, they gave me the pH, right? So I'm going to say POH equals 14 minus 9.37, which is 4.63. That means that OH minus concentration equals 10 to the negative 4.63, which I found to be 2.34422, a bunch of numbers, times 10 to the negative fifth. And that's equal to my OH minus concentration. Okay, so that equals X. Again, I'm looking at this being OH minus concentration. Okay, I'm going to finish this down below because I'm out of room. So this means that Kb equals x squared over 1.0 minus 2.34422 times 10 to the negative fifth. And actually, x squared is the concentration of the acetic acid times the hydroxide, which would be X times X, which is going to be this 2.34422 times 10 to the negative fifth. I left this in my calculator and just squared the answer to what I had above and then divided that by, in parentheses, 1 minus that answer again. So I got a KB equal to 5.49, whoops, 55, a bunch of numbers, times 10 to the negative 10th. I have two significant figures from my 1.0 molar and my pH of 9.37. So that means that my KB is going to be 5.5 times 10 to the negative 10th. Now, I could just say, we know this is the answer, but let's check this. If you were told that Ka for acetic acid is 1.8 times 10 to the negative fifth, remember that you can use Kw to find Kb from Ka. So Kw equals Ka times Ka times Kb. So this would be 1 times 10 to the negative 14th equals the Ka, 1.8 times 10 to the negative fifth, times Kb of the acetate ion. So I solved this by dividing by 1.8 times 10 to the negative fifth, and I got 5.555, a bunch of numbers, all fives, times 10 to the negative 10th, which would round to 5.6 times 10 to the negative 10th. So this is really close to what I found up here as the Kb from my math. So this is just going to be from rounding. And because this 1 times 10 to the negative 14th would round a little bit differently, etc. So this is I'm pretty confident that what we did up above is correct. So hopefully, now that you have a good background of Ka, Kb will be pretty straightforward and pretty easy. And we'll do some practice in class, and then we'll move on to how we use that when it gets a little bit harder.